Now let's look at another example of decision tree. Let's say you go to a casino and there's a game to play. This game costs you $60 of admission to play. If you decide to play the game, all you need to do is to flip a coin. If the coin shows head, you move on to step 3. If it shows tail, you move on to step 4. In step 3, you will flip the coin again. If it shows head, you get $20. If it shows tail, you get $120. The game ends. Step 4 is as follows. You can choose to walk away with $20 for sure or flip the coin again. If you choose to flip the coin again, then if it shows head, you get $10. If it shows tail, you get $60. The game ends. The question is quite simple. Should you play the game? Now let's build a decision tree for this problem. Again, when you build a decision tree, all you need to do is to build a tree from left to right following the sequence of events. And the events we're interested in are decisions or uncertainties. Okay, so let's look at this problem. First, it says, well, there's a game cost $60 to play. There's really no decision so far, no uncertainty so far. Second, if you decide to play, you flip a coin. Okay, what do we have so far? What we learned so far is the first thing you need to do, the first event is actually a decision to play or not. So it's a decision. So I'm going to use a square to represent that decision. And the choices are to play or not to play. So I'm going to give it two branches. One represent playing, the other representing not to play. Okay. For each branch, I simply need to think about, so what's the next event? If I decide to play, what's the next event? Before actually thinking about the next event, I noticed that, well, the game costs $60 to play. So that means if I decide to play, I need to pay $60. And I'm going to mark $60 here, negative 60. Negative simply means it's an expenditure, okay? Because I'm measuring in the end, I'm going to use my profit as my payoff. I'm spending $60, so it's a negative $60 in terms of profit. Okay, so why am I going to put this negative 60 here? Okay, this is a good practice. Whenever some cost, some revenue, something that affect your payoff is happening along the line, I encourage you to just note it as they occur. Okay, this is a good reminder. You will see why later. Okay, so I marked minus 60 here simply because when I decide to play, I have a profit of minus $60. Okay, so after I decide to play, what's next? It says you will flip a coin. So flipping a coin, there are two possible outcomes from flipping a coin. Okay, and I cannot control the outcome from flipping a coin. So that means it is an uncertainty. It's not a decision. It's an uncertainty, so I'm going to use a circle to represent this uncertainty. Flipping a coin has two outcomes, so I'm going to give two branches out of this circle to represent the two outcomes. First, I may see a head. Second, I may see a tail. Okay, so two branches. Remember, when you have a circle, it's an uncertainty. In the case of uncertainty, you also need to mark the probability for each possible outcomes. So let's assume we are flipping a fair coins, which means the chance of having a head or tail is equally likely, 50-50. So I'm going to mark the probabilities here. Now, for each branch, again, I'm going to think about, so what happens next? Let's start from this one. If I flip the coin and it shows a head, what happens? It says, in that case, you will move on to step 3. Okay, so let's look at what happens in step 3. It says you'll flip the coin again. Okay, so flip a coin again. Again, the outcome is not something I can control, so it's an uncertainty. So I'm going to use a circle here because there's an uncertainty. Flipping a coin, again, there are two possible outcomes. It can be either head or tail. Again, marking the probabilities. And now it says if it shows head, you get $20. If it shows tail, you get $120, and the game ends. So that tells me at this point there's no further events and the game ends here. But it also tells me if it is a head, I get $20. If it is a tail, I get $120. You know what? I'm going to mark $20 here, and I'm going to mark $120 here to tell me that actually if I end up here I get $20. If I end up here I get $120 here. Okay, and you will see the benefit of marking the numbers here very shortly. Okay, I'll talk about that later. But now let me move on to this branch. Here, if the first flip is a tail, what happens next? Over here it says if it is a tail, you move on to step 4. So let's look at step 4. It says you can choose to walk away with $20 for sure or flip the coin again. So the key word here is choose. You choose to walk away or flip a coin. So that means the next thing after seeing a tail here is a decision. So I'm going to use a square. Square represent decisions. And how many options do I have in this decision? Well, there are two. Walk away or flip a coin again. Okay, so that's why I have two branches. And if I walk away, it says I get $20. So I'm going to mark $20 over here. So I know I'm going to get $20 here. And there's no further event if I walk away, so that's it. But what about tossing the coin or flipping a coin again? Well, it's another uncertainty. So I'm going to give you a circle, and there are two outcomes, head or tail. Again, it's a circle, so don't forget to mark the probabilities. It says if it is a head, then I get $10. So I'm going to mark $10 here. It says if I get a tail, I get $60. So I'm going to mark $60 over here. Okay, so there's no further event. So basically this is a structure for the tree. Now I need to mark the payoffs for each branch. So here each branch represents a possible outcome of the game. So there are 1, 2, 3, 4, 5, 6 possible outcomes. First outcome, okay, that means we decide to play. First flip shows a head, second flip shows a head. In this case, what's the final payoff? Well, this is a place where you find those numbers very convenient. If you decide to play, you pay $60. You go here, nothing happens, and then you end up here, you get another $20. So in the end, that means your total payoff is you spend $60 and then you get $20. So that's negative 40. That means if you decide to play, first flip is ahead, also second flip is ahead, then you will end up losing $40. Likewise, let's look at the second branch. Here, this represents you play. First flip is head, but the second flip is tail. In this case, you spend $60 in the beginning and then you get $100 in the second flip. So your total profit or payoff is going to be $60. Next one, you play, you pay $60, showing a tail in the first flip, and then you decide to walk away getting $20. So the profit or the net payoff is 60 minus 60 plus 20, so minus 40. Next one here, that means you pay $60, get a tail, decide to flip a coin again, and then get $10. So you end up losing $50. Likewise, this one, You pay $60 and then get $60 here, so you end up balancing out. Okay, 0. If you decide not to play at all, you don't pay anything, you don't get anything, so your payoff is still 0. So now at this point, we have constructed a decision tree for this problem. So that's just the first step. Second step is to analyze this problem. We call it fold it back. We are going to fold back this tree from right to left to find out the first decision, whether you should play or not. Okay, so I'm going to mark the nodes so it's easy to, just for ease of reference. Okay, so you're going to analyze the node from right to left. Let me start off from this node 1. So if we end up in node 1, then this is an uncertainty. We either get head, which means we have a payoff of this, or we get tail with a payoff of this number. It's an uncertainty, so that means we need to calculate the expected payoff of this node. So the expected payoff, again, is simply probability times payoff plus probability times payoff. Okay, so it's over here, comes out 10. I'm going to copy that 10 next to this node just to remind me. If I end up here, my expected payoff going forward is $10. Okay, now let me move on to another node. Well, I need to move on this one because this is another end node that doesn't have any following node on its right. Okay, so again, similarly, it's a uncertainty. So what I'm going to do is probability times payoff plus probability times payoff. So that gives me an expected payoff of negative 25. So I'm going to copy that number next to this node, so I know if I end up here, going forward, my expected payoff is negative 25. Now I can move on to next node. Can I move on to node 3? No, I cannot, because if I need to analyze this node, I need its payoff from every branch. I have this one, but I don't have the payoff here yet. So next one, I really need to look at this decision. In this decision, I can choose to walk away and get minus 40 or flip again, getting expected payoff of minus 25. Apparently, this number is larger than this number, so that means choosing to flip again is a better decision than walking away. So I'm going to choose this branch over here, and I'm going to copy the payoff of this number next to this square to represent that if I end up in this decision, I would make a decision that ends up with this payoff, expected payoff. Okay, now I can move on to analyze the next node over here, node number 3. So in this node, I have two possible outcomes. It's a circle, so I need to calculate its expected payoff. Here, if the outcome is head, my expected payoff will be 10. If I end up a tail, my expected payoff will be minus 25. So the expected payoff is simply probability times payoff plus probability times payoff. Okay, which comes out minus 7.5. I'm going to copy this expected payoff next to the node. Okay, so I know that means if I choose to play, then my expected payoff going forward is minus $7.5. Okay, now I have all the nodes. I can move on to the next one on the left, which is this decision. There are two options here. If I choose to play, my payoff going forward is going to be minus 7.5. If I choose not to play, it's 0. So I'm going to maximize my expected payoff. Okay, 0 is larger than this negative number, which means I should choose not to play. In that case, I get 0 payoff. Okay, so at this point, we finished the analysis of this whole tree. We fold it back and conclude that you should not play the game.